welcome to this video. We're going to do number 2 from the data analysis questions. By the way, you'll see this in this problem. Datum is singular, data is plural. But maybe data could be singular too? Check your grammar rules. Anyway, Gillian, this person Gillian, she carries out an experiment to investigate craters when steel balls are dropped into sand. She's dropping a ball into sand, it makes a crater, she's looking at that. To try and find the relationship between diameter of the crater, how big is the crater, how long across, and the energy of impact, she dropped a steel ball from different heights into sand and measured the resulting diameter d. So the higher up you drop it, presumably, let's see, bigger the height, 2 is bigger than 0.5. The bigger the height, the higher the diameter. So dropping the ball from higher up makes a bigger crater. The data are shown below. Data are, that's plural, right? Okay, the uncertainty in the measurement of d, presumably every measurement of d then, because they don't specify which d measurement. Right, here's a d measurement, here's another one. Every measurement of d has this uncertainty. That's funny. It should be, maybe, plus or minus 0.4 centimeters, just 1 sig fig. The uncertainty in height is too small to be shown. Height. So there are no horizontal error bars. There's no uncertainty on the x-axis. Draw error bars for the data point, 0.2, and this, and then also for 2, 0.10. Okay, where's the data point 0.2? This right here is 0.25 because it's halfway between 0 and 0.5, so this must be 0.2. So draw error bars. Well, there's no horizontal error bars, right? Uncertainty in h can't be seen. So we only have to draw vertical error bars. So go up 0.4 and then go down 0.4. How many blocks up and down do I go? This is 2. We've subdivided it into 1, 2, 3, 4, 5 little blocks. So what's that going to be? 0.4, right? 2 over 5. Alright, so that's the uncertainty. I need to go up exactly 1 block. So starting in the middle, go up to the middle, and down exactly 1 block. And likewise for this guy here, 0.1, where is it? Oh, no, sorry, the x value is 2, x value of 2. That one, I need to add the same sized error bars. Up a block, down a block. Right, like that. Draw a best fit line for the data. This sure looks curved to me, and I think I could send it through the origin. Oh, wait, I have to. Look at this. There's a data point right there. I have to send it through that data point because the error bars would be like, pretty small. And it has to go through all the error bars, right? So let's try this like so. Oh, gosh. That's decent. The way you do this is you do it in pencil first, and then once you have a good line, you go back over in ink, in pen. So that's how you draw these lines without, messing up in pen and then scratching out. Because you can't scratch out, it looks bad. Got this, got that. The original hypothesis of Gillian's was that diameter, d, is directly proportional to the energy of impact. Directly proportional? Oh gosh, this is certainly not proportional. Well, let's do this. First, let's talk about not energy, but height. D is not, and explain why the data does not support this hypothesis. We're explaining, we're not showing, using the graph. So explain means like with words. So first we say D is not proportional, or directly proportional you could say, to the y and x to x. What's x? The x-axis is height. D is not proportional to h because it isn't possible to draw a best fit line or just a line that is straight, passes through the origin, and passes through all the error bars. Well, but that's not what they asked. They asked about energy. You see this? So here's the key. This requires remembering that when you drop from a height, the potential energy is equal to m times g times h. So if d is not proportional to h, it's not equal to a constant times h, then it's not going to be proportional to the potential energy, because m and g are constants, right? You could just pack those in right here and change h. You could change h to potential energy. Another way to see this is d is not proportional, it's not equal to a constant times h. H can be replaced with Pe over mg, right? H can be replaced with Pe divided by mg. And then mg and k could be combined into a new constant. So you see d is not proportional to potential energy. So since the energy equals mgh, d isn't directly proportional to energy either. Because Gillian's data didn't support her hypothesis, she researched to find an alternative hypothesis. She found two theories, and then she plotted data to test both. The first predicts that d is equal to a constant times h to the 1/3. So she plots d against h to the 1/3. If she gets this, then this is correct. We don't know yet. The other says d is proportional to h to the 1/4. So she plots d on the y, h to the 1/4 on the x. And she's looking for a graph that does this. Draw a best fit line on each graph. Alright, let's see. I'm looking at my error bars. I'm through all the error bars. Then I want to try and get it as close to all the data points as possible, right? And I'm thinking, can I send it through the origin? Let's see. That looks decently. That looks okay, you know? That doesn't look too bad. Let's try this one. Oh, this is clearly not through the origin. This is definitely not the graph that Gillian wants. Gillian, come on, Gillian. So let's do this one first, because this is clearly failing to be directly proportional. And then we come back up and say, okay, then this must be the one that's directly proportional, right? So send this to the origin. Is that good? Pretty good. State and explain which theory is best supported by the student's data. Well, the first is better supported. It should be better, not best. There's only two, so better is better supported. I stated, now I have to explain why. Because the first graph of, what is it, d against, instead of versus, IB likes the word against. It's always y against x. D is on the y, against x is h to the 1/3. The first graph is straight, passes through all the error bars, and goes through the origin. That's what you write. Good. And that's how you do number 2.